Okay, looks like we're going to get started. Everybody enjoying the day outside? It's good? Excellent. Okay, we don't, very quiet crowd here too. Okay, so I'm going to talk here about moving to the G1GC garbage collector. I'm going to warn you in advance, this is not the typical introductory talk that you're used to seeing for garbage collectors. I hope to get a little bit deeper. So if we move too fast, you can shout at me and, oh my God, what did they do to the lights here? Turned it down, I guess. Okay, whoa. So anyways, if I get a little bit too far ahead, I can't see anybody, so just scream at me saying like, what does that mean, okay? And I'll try to back up and go a little slower. So the about me. So who am I? Well, I'm Kirk, Pepperdine. I write about performance tuning, offer performance tuning services training, and we have a tooling company called J Clarity, which we started in London, which interestingly enough does a lot of things that you heard Rod Hardrup talking about this morning, actually. Whole bunch of other things. Typically I say use Google. If you like what's happening, then you can tweet things about it, right? Okay, so there's a bit of news here, and there's things that Oracle really hasn't made a big public splash about. And the first piece of news here is that the G1GC will be the default collector in Java 9. So as you move forward to Java 9, if you don't specify a garbage collection combination, then this is what you're going to get, right? Do people know what they're using now for garbage collector technology? Few hands go up. Anyone using like parallel CMS? Does people know what CMS is? Shout out what CMS is. Excellent. You've all recovered from your food coma. That's good. Yeah, it's a mostly concurrent mark sweep collector and everything like that. Yes, and so since we all love that collector, because everybody here just loves it, the next bit of news might be a bit of a downer, a bit depressing. I suggest you go out and get some sun after this, right? Because in the next release, CMS will be deprecated. As far as I know, the problem is like no one's really said much about this, and a few people are kind of like unhappy about it. But just basically over the weekend, we had a JEP come up, which is it's a Java extension proposal that basically suggested that the concurrent mark sweep collector be deprecated. Which is really not surprising because everyone believes that the G1 collector is actually ready for prime time. And the question is it really ready for prime time? Well, the answer is, yeah, it sort of is, it sort of isn't, So there's some questions, right, that we need to ask her. What does a regional heap look like? How do the algorithms work? And how does the performance compare to other collectors? And what is there, is there any hints that can possibly give you to help you tune it should you have to tune, this particular beast? And that's what we hope to get through in the next couple of minutes. So just to remind everyone what a generational garbage collector sort of looks like, well, at least the data structures, you can see that we have a nursery called Eden. And we have these two other spaces called S0, S1, which is your survivor spaces or your two from spaces. And altogether, those make up the young generational space. And then we have a old generational space, or what we call a tenured space, which would be the other blue part. And it's all of these spaces that make up our Java heap currently. Now, in the young generational space, we do what's known as an evacuation collection. So we'll do a mark sweep, and we'll identify all the live objects and evacuate them someplace. In tenured space, we have what's known as an in-place collection, which means at the end of the collection, there's still data is residing in the tenured space in that particular memory pool, right? Okay, and this all really worked really well. It gave us some really reasonable results until people started deploying applications in 64 gig, 128 gig, 512 gig, right? You know, and until we get into these like extra large heaps, and then we start running into problems. We have like some scalability issues that we have to cope with. And really the scalability issue is that the pause time that we're experiencing while, you know, the garbage collector runs around and does whatever it has to do tends to be linear with the size of heap. So the bigger heaps you have, the longer pause times. You're going like, okay, so, you know, that's not good. And there's other issues, like the CMS collector was fairly difficult to tune. It comes with a lot of like what I call esoteric command line parameters, like this one here, TLAB waste per target percent. Does anyone know what that is? Right, exactly. We have chuckling in the front, and that's probably what people, you know, if you're, you know, what is like TLAB waste target? Anyways, you know, whatever that is, you know, I'm sure, you know, somebody on Stack Overflow has said you should set this to some particular value, and then somebody's gone off and done that, and, you know, who knows what happens after that. Right. The other thing is, like, it's completely unpredictable, and people were saying, like, you know, we want predictability. And, well, at JClarity, we were working with a client, and they basically were trying to get rid of us. So they said, can you give us some predictions as to what's going to happen? You know, thinking like, okay, we'll go away because we can't do that. In reality, what happened is that we found it was fairly predictable, and with a greater than, it was somewhere between 80 and 85% accuracy, we could predict what was going to happen within the next 3 to 5 minutes, which, you know, which is pretty good. I mean, you can do stuff with that duration of time. But anyways, that's a completely different talk. So we won't talk too much about that, right? So these are some of the problems we had. So we end up with this thing called G1. G1's designed to scale. So if you want to deploy a 1 terabyte heap, for whatever reason you want to deploy a 1 terabyte heap, you can go ahead and do it, right? I think there's already some people actually doing that for some reason. And you're not going to have a pause time that's linear to the size of the heap. It's linear to other things, but not the size of heap. Supposedly easier to tune, although it's taken me 2 years to figure out how to tune it, right? And I'm not sure I know many other people that actually do know how to tune it yet. Maybe in some cases. You know, hopefully it comes out of the box and it just works. And if that happens, and that has happened, then life is really, really good. Yeah, so fewer configuration options. There's certainly fewer configuration options, but I would say that they're maybe only slightly more understandable than a TLAB waste percentage. And predictability. So they're going to offer you some way of saying, like, I would really like my pause times to be less than X. If you can possibly do that, that would be like really wonderful. And, you know, it will make every effort it can to actually try to meet that particular pause time goal, right? So what does this thing look like? Well, I have a whole bunch of slides showing you how it all looks like. But then I managed to convince one of my customers to turn on some extra esoteric logging flags and generate some very, very large logs from their production systems. And I can show you exactly what it looks like because we can just look at a nice visualization that I have from their production system. Now, before we start, we can say, like, you know, first off, you know, this thing looks similar to a generational heap in the sense that we're going to get one large contiguous space, and then we're going to chunk it up. But instead of chunking it up into about 5 chunks, we're going to chunk it up into approximately 2,048 chunks. Well, somewhere between 2,048 and 4,096, right? And we're going to do that based on the size. Well, there's the calculation. You can look at the calculation there and read it. But you can see with a 10 meg heap, you end up with about, you know, the calculation says 5 megs, rounded down to 4 megs. That means we end up with 2,560 regions, all, 4 megs in size. There's a slight error on the slide there. That should not be 4G, it should be 4M. Sorry about that. Right. So anyways, the region sizes can be any one of these particular sizes, like 1, 2, 4, 8, 16, 32, or 64 megabytes. Okay, now, with that ado, let's run some funky code here, right? Okay, so, takes a second here. What's going on? Can we see it? No, you can't see it. You can just see other funky code I have up there. Let's get rid of that and take this down. So I slowed it down a bit, so I don't know if it's too slow. But essentially what we're looking at here, can I make that bigger? The application is it's allocating regions. See if you guys in the back can actually have a chance at seeing what this thing looks like. Yeah, I just threw this together quickly, so I haven't put the legend on it yet or anything like that, some controls. So there's a few things I want to put on it, then I'll drop it into GitHub so you can play with it. But so what happens is I'm going to put all of the regions on the free list, and then at the beginning of the collection cycle, I'm going to say, well, I'm going to put so many regions up for Eden, so many regions up for Survivor, so many regions up for tenured space. So in this way, it looks like a generational collector, right? But I'm going to put so many, I'm going to allocate so many, or to assign so many regions to each of these spaces, and then say, okay, I'm going to start allocating. So as I'm allocating objects, what I'm going to do is go to the free list, grab a region, allocate till it's full, or I've hit a waste percentage value where I can say, okay, go get me another region and keep doing this, right? And so if you look at this thing here, you can see what's happening on the list is that the green guys at the bottom, or mostly at the bottom, those are Eden spaces, right? So I'm going to take it off the free list, and I'm going to take that region, I'm going to tag it as being an Eden space. The yellow is my Survivor space, and I only end up with one, so that's the 2 space actually. And the blue guys, that is my tenured space, and the black guys, right, those are my unallocated regions, which leaves the coral and the red things to explain, right? Okay, so these are pretty easy. The question is, what happens if we allocate something larger than the size of a region? Now we get a problem, right? Because that is actually going to be a buffer overrun if we just do the allocation proper. We don't really want to do that, so what I'm going to do is I'm going to say that anything larger than half the size of a region, I'm going to tag that as being a humongous allocation. I'm going to treat that one special, okay? So the coral is actually a humongous allocation start, and the red bits are actually a humongous allocation with the continuation of that humongous allocation. So you can see there's one stable humongous allocation in this particular application way up at the top, and that's possibly simply something as simple as a cache, right? Cache started up at the beginning of the application or somewhere near the beginning of the run, and it's a large array of something, and I'm allocating stuff in, the stuff's going into the cache, coming out of the cache, however that works, right? And you can see that's been treated as one humongous allocation, and it's generally not moving around. It's just staying right where it is, because I'm not going to do anything. I'm not going to touch these particular regions. And the other ones are bouncing around. They live for a few garbage collection cycles, and then they disappear. For me, when I started looking at this visualization, it was a bit surprising, because I was very surprised that, one, they segregated out the young generational regions from the tenured space regions, so they tend to come from the bottom of the list, where the tenured regions come from the top of the list. But then, what happened? Oh, we're at the end of it. Okay. But then the other thing you can notice is that the humongous regions get mixed up with the tenured regions, and well, when we get more into the discussion, you're going to say, okay, you'll probably yourself start asking the question, like, why did they do that? Especially since we have this large black gap area in the middle here that it seems like we could be making better utilization of. Okay, so let's go back to some slides and see what's going on here. Thought I had some, there we go. I can read what's going on also. So where are I? So these were the kind of things that we're talking about here. So the free regions kept on a free list, and then they're just allocated out. So I'm not going to go through any of this thing here. Okay. So now we have garbage collection triggers. Okay. So what actually triggers this garbage collection cycle in this particular scheme? And so for young generational collection, we're just going to use up all of our regions. When we've used up all our regions, bang, we're going to just run a collection, right? For a collection of tenured space, that happens very differently here. Now, for young generational collection, what we're going to do is a mark, sweep, evacuation. So we're going to take find the live data in the mark, and the sweep is going to evacuate the live data into a new set of regions. And I think you could see that because the young regions were flipping up and down, right? They're coming back and forth. So you can see that all of that copying going on there. With the tenured space, this thing happens differently. What we're going to do is we're going to set what's known as initiating a heap occupancy fraction, or percent. So the acronym is IHOP, which coincides with a very bad pancake house in the US, unfortunately. But anyways, that value is 45%. So when the tenured space gets 45%, gets filled up so that it occupies 45% of heap, then that's going to trigger a concurrent mark of all of the tenured regions. Okay? So the mark is now going to calculate an occupancy percentage of each of the particular regions. So how much of this region will be occupied by live data after I do the collection. Okay? Next, what we're going to do is we're going to sort those regions, and I'm going to cut the list off at a particular threshold, an occupancy threshold. So if the region is more occupied than that particular threshold after the mark, then I'm just going to say, okay, I'm not going to bother considering sweeping those regions. I'm just going to take the ones that are lightly occupied, right? And not only that, the tenured space collector is not even going to actually do the sweep. It's going to take all of that set of regions, and it's going to add them to the young generational collector. So the young generational collector will actually be responsible for sweeping the tenured space regions. So what happens is, now this is where the time budgeting comes in. I'm going to look at each of the regions, and I can estimate how much time it's going to take to sweep that particular region. So what I'm going to do is I'm going to build a collection set. What goes into the collection set? All of the young generational regions, so that's Eden and Survivor. And in what's known as a mixed collection, I'm going to add in a portion, or maybe all, of the tenured space regions into that collection set. So I'm just going to go right up to my time budget, and then I'm going to cut it off. Okay? Now, there is another thing that happens here. There's another constraint, and it says that I have to be able to sweep all of the tenured regions within 8 collections, right? That's a configurable value, but I can break this up into a maximum of 8 regions, which means that if I have too many regions to sweep, so that I'm going to blow my time budget, whatever it is, then I'm going to blow my time budget. Okay, and that's pretty much how the collector works. So we have collection triggers, right? We fill up Eden is the first one. Second one is we fill up heap completely, and that would trigger like a full GC, and a full GC in this environment is something you never want to see. It's generally a very devastating event. We hit the IHOP, that'll trigger a mark of the tenured spaces. Or we have another thing, which is a metaspace threshold is reached, right? And that's sort of off topic for this particular talk, right? But there is metaspace for the metadata, and if we hit that particular threshold, then that will also trigger a garbage collection. Okay, so YoungGen is going to be a complete mark sweep, and when we hit the IHOP, it'll signal that we need to do a mark of tenured, and the mark of tenured is mostly concurrent. It starts with an initial mark. The initial mark will be piggybacked on the young generational collection, and then you're going to see here's all the phases. The green ones are concurrent, the red ones are stop the world phases. Right? So it's pretty much as you would expect. First thing I need to do is I need to do a scan for roots. Once I find the root sets, then I can do the mark, the initial mark, which means that I'm going to step in away from, well, the technical term is I'm going to internalize all of my external pointers, because my external pointer set is really my GC roots for each of the regions. And once I've done that, then I can let the world go, let the application run, and I can continue to do the marking until finally I'll do a stop the world phase where I'll actually do a remark. As marked in green incorrectly. Sorry about that also. Right, okay, so that's pretty much all of the phases. Now, we have a scan for root problem here that we haven't discussed. The scan for roots means I need to go for a particular region, and I need to find all the external pointers. That is, all of the pointers that are originating outside of that region that are pointing to data inside of the region. Yeah? So where am I going to find them? I'm going to find them in every other live region in the system. I'm going to find it in stack frames. I'm going to find it in code roots. I'm going to find it in registers. I'm going to find them in globals. So I'm going to go through all these different places and find the root set for that particular region. Okay, that doesn't sound like we've broken the linearity problem with the size of heap, right? It sounds like we made it worse, because I need to do that for every individual region in the system. Okay, so how are we going to manage that? Well, what they've done is they set up a different data structure known as a remembered set. And the role of the remembered set is just to remember, or to record, all of these external pointers. So instead of having to scan all of heap to find all of the pointers, what I'm going to do is I'm just going to go to the remembered set, and I'm going to grab that set of pointers, and that's the start of my, of my GC roots. Okay, and then I'll have to scan the other places, the stack frames and things like that, to find the rest of them. Right, so that'll be my starting point. Now, the RSet data structure is a fairly complex one. I don't want to really get into it too deeply. Just to say that it's a dense representation of a very sparse data structure, which means that there's a lot of work that has to be done to get these pointer values actually into the remembered set. So we don't want the mutator threads doing that, because that's a lot of work. As a matter of fact, the work is non-linear with the size of the region, which is another issue. But that's the way it is right now. So instead, what the mutator threads are going to do is every time you do a mutation where you change the value of one of these pointers, we're going to queue that into an RSet refinement queue. And there's going to be RSet refinement threads that are going to work to take these pointer values out of the queue and then put them into the RSet proper. Now, as you can see, I got a white area, a green area, a yellow area, and a red area. And that basically, as we move towards the red in terms of fullness, the JVM is going to get more and more aggressive at trying to clear out this particular RSet refinement queue. When you get to red, it's going to actually start engaging your application threads to clean the queue out. Okay, C-sets we've talked about. The slide there, promotion in, that's parallel phases. Right, so for the phases and everything like that, I think some, at this point I'll probably just flip to a GC log, and you can see the phases and their effect on, or their contribution to the pause time. So, excuse me. Flags you probably want to use. So, specify use the G1GC, although that won't be necessary 9. Specify the heap size, and possibly give it the pause time goal, right? And of course, I always recommend turning on GC logging because that gives you a very good indication into the memory health of your application. Flags you might want to use. You might want to set the region size yourself. So here's where we would do that. If we have a lot of humongous allocations, but say they're only like 1 meg, and we have like 1 or 2 meg regions. Well, I can get rid of those humongous allocations by just setting the region size to 4 megs, right? Because the humongous allocation is something that's half the region size. So, boom, problem goes away just by some configuration. Initiating heap occupancy percentage, so we can raise that or lower that. And there's arguments to go in either direction. I'll make some recommendations a little later on that one. And this collector is highly adaptive in the number of regions that it will actually allocate to each of the generations. In particular, the young generational space is allowed to shrink to 5% of total heap. Now, I've worked on a submarine project where we actually wanted to lower that value, and I've worked on many other projects where we actually wanted to raise that value. The reason is, generally the pause times are going to be some function of the size of of Eden. And so if one of the triggers or one of the controls we have on pause time is actually how small we can set this particular space, right? But there's also an overhead cost here. If we make it too small, then of course we're going to have frequent collections. If we make it too big, we're probably going to have longer pause times. But big means less frequent collections, which means less overhead. So you can see there's a couple of tensors here that we have to balance against. And of course there's a few other flags where you can get extra bits of information. Flags you should think twice about using. The G1GC target count, we have played with this. So one of the things I've done is actually taken the IHOP value, dropped it into the floor, right? So that you're actually just riding right at the edge of the live set, so you get like frequent mark cycles of tenured space, and then up this thing here, and there's another parameter that's in the list of flags you should never use. We actually play with this one to basically say, let's be more aggressive about collecting the tenured space regions. And that's the bit about, what is it? G1 old, yeah, this thing here, right? So in this case here, what we're basically saying is like, let's make sure that, more regions actually get considered for collection. Let's make sure that the collections happen more frequently of these things. And so let's make the number of mixed collections that we can perform actually larger, so we can break this data set up so that we can end up with smaller collection sets so that we don't suffer from horrendously long pause times. So there's this sort of balancing games that you end up playing, trying to figure out how to tune this thing, which is why it's so difficult. Well, that, and they keep changing the implementation on a build-by-build basis. So you're chasing a moving target at the same time. Okay, things that give us grief. RSet refinement. Sometimes if your mutator threads are just going nuts mutating things, then that'll put a lot of pressure on the RSet refinement threads to eat down the queue. And if we call for a garbage collection and there's stuff in the RSet refinement queue, the garbage collector threads have to finish the job before the garbage collection cycle can start, right? Object copy. Now, when I wrote the slides, I said not much to say there, but I've since changed my mind on that, so I'll give you some information on that in just very shortly. Humongous allocations. These used to be really, really bad. If you had a humongous allocation and you couldn't allocate because you didn't have enough contiguous regions to satisfy it, then that would trigger a full GC. Obviously not good. So what to do in that case? Well, of course, we had to play with the region size, but then I said our updates are nonlinear to the size of the region in terms of costs, so you didn't really want to do that. So you're really sort of stuck. You know, you go this way and you'd hit the wall, and you go that way, you'd hit another wall. Now, what they did recently is they said, okay, no problem. We'll try to solve this with a young generational collection, right? And they'll try a young generational collection. If they solve it, cool. If not, they'll run another one. If not, they'll run another one. If not, they'll run a full GC, right? So, you know, one of the things we've done is actually gone back into applications and broken up some of these data structures and fragmented them and segmented them so that we can actually get smaller allocations without actually having to adjust the region size. Another thing that this thing will give you grief is this thing called notion of floating garbage. We'll call them zombies, right? This is data that's dead, but it is pointing to other data. So you have data in one region, it's dead. You're trying to collect this region over here, right? So we don't know this one is dead. And so what happens is that we still have a pointer from here to there, but it's live as far as this guy is concerned, which means instead of the data being dead in this region, it's live and it's floating. Now, as soon as we collect this region, we'll know, you know, this data is dead and should be collected when we come back around to get this particular region. But until that happens, we still have to treat this data. We still have to interact with it. It takes CPU. And you get some really interesting effects. You'll see pause times just climbing like this. We'll do a full GC, they'll hit the floor, because full GCs are always exact. And it'll go up again like this, bang. And you can actually do some calculations as to how much dead data is in heap by just looking at the effect on pause time, right? Or the drop in pause time after a full GC. If you are unlucky enough to suffer from them. And really, the floating garbage has a negative impact on the object copy costs, and the object copy costs are the costs that tend to dominate, right? So, and this is why we want maybe more aggressive ripeness settings. So, you know, so how much of a region has to be occupied after the mark before we'll actually consider it for being collected. Okay, so those are the things that will give you grief. So with that in mind, we took a look at Cassandra. And we said, okay, so out of the box, the Cassandra benchmark is tuned to use CMS. And I said, okay, well, let's take a look with G1 and see what we can do. So I gave it a fixed unit of work, completely saturated the CPU. Not the way you should run a benchmark normally, okay? In this case, what it allowed me to do was measure G1 overhead relative to CMS. So if this thing is running at 100% CPU, and I'm giving it a fixed workload, then really what we're saying is like, okay, what's the throughput of this thing? Well, it's going to be, you know, what's going to take away from the throughput is going to be the overhead of the garbage collector. And so we ran it this way, and you can see the first point out here, that's the CMS run. It's nice and high. It's got the highest value, so that's really good throughput. And then everything I could do afterwards to the G1 collector, you can see that with all of these runs here, making different modifications, it could never really get the throughput that we got with the CMS collector. So it is running at a higher overhead. You know, so the next set of benchmarks I'm going to run with this thing is obviously going to give it enough CPU so that we can actually tune this thing to see how it actually runs when it's got enough overhead to, you know, well, enough clearance in order to do the job properly. Now, there is one point up there, which I can point out, this one here, which is riding very high. And so, you know, how did we get that point to actually ride higher than the rest, which is an interesting thing. So if I come back over to, that's this one right here. Okay, let's take a look at this GC log here. Whoops. Let me help you by putting it up on the screen. Now, I'm going to make this smaller so we can zoom in, and hopefully the people who are up in the nosebleed seats actually have a chance of seeing what this data actually looks like. But I'm using this funky scrolling mode, which sometimes decides to take off and do goofy things. Okay, so this is our tooling Sensum that we wrote for doing GC log analysis. And as you can see here, we ingest the GC log and we actually do a lot of stuff on it. I mean, one of the things that we actually do, which I'll just give you a quick, is we'll see we can look at a lot of different metrics that we have, like just analytics. So, for instance, this one's complaining about high kernel times. So, we use this analytic to help determine if your JVM is suffering from what we call noisy neighbor, right? If you're running in a VM and you have lots of steal time and stuff like that, we can pick that up with this particular analytic. Anyways, that's small aside. Okay, so if we come back over here, you can see there's our summary. We're running at an application throughput of 93.8%, which means that the garbage collector was running for is that right? Yeah, 6.2% of the time. Whoa, that's nice. Thanks, AV guys. And you can see over here we have these are the pause time events. So we have, there's our young generational collection, there's our young with the initial marks, our remarks, our mixed collections. So you can get an idea what's going on as to actually who's, sorry, I hit the bottom, which I shouldn't have. You can get an idea who's actually contributing to the overall pause time. You can see it's actually the young generational collections that are heavily responsible for what's going on. So you can look at different metrics here. You can see, okay, this is heap utilization after GC. It's completely stable. Nothing to see here. Let's move on. And really, if you look at all the other metrics, well, here's some pause time metrics, and you can see there's one that seems to be above what I would consider the pause time goal of 200 milliseconds, but it's really these collections here that are fairly long. All of these other ones are fairly short. So you can, anyways, we can do a complete analysis of the whole thing, but let's get into the interesting part, and let's just say here are the G1 young generational phases that were reported in this particular log. So we have a code root purge, a clear the card table, that's actually remembered set work, right? We have some other things that are miscellaneous things that are happening that are not categorized, and that'd be like string table maintenance and things like that. There's no string deduping in this particular benchmark right now, so that's actually not showing up here. Code root fix up, parallel, so and if you look at it, the dominant phase really is the parallel phase, right? So, okay, so what's happening there? So I'm just going to go past the parallel phase and go into parallel percent. And if we look at this, we can see, okay, there's snapshot at the beginning filtering, so that's our initial view as to where we start our collection from, or sorry, our mark phase from in tenure space. Thread termination, these are all in the floor. It's really like what are these like gray circly things? That's external, whoops, damn, did it again. Hate when I do that. External roots scanning. So this looks like a startup anomaly, because really the big problem in this particular log is object copy time, right? One of the problems that I said that I didn't have much to say about at that particular time. Yeah, so there's an object copy problem in this thing. If we go into GC cause, we can actually see there's another issue here too. In particular, if we look down here, we can see that all of this blue stuff, those are all collections that have been triggered from humongous allocations. All right? So we still have a lot of humongous allocation happening in this particular application. So we might want to do some memory profiling to see where this is happening, to see if we can break that down or try to prevent this particular behavior. Okay, but really the big thing on the block is, okay, so this is the object copy time. Okay, so what can we do about that? Let's go back to some slides here. Where are we here? Okay, so has anyone heard of this thing? The weak generational hypothesis? No? Objects die young, yes, exactly. So most of the data that you use, you create it and you immediately throw it away. Most of it is not referenced by the time it leaves the CPU. If it happens to be still referenced by the time it leaves the CPU, it's going to live for a very long time. So that's on the other end of the chart here, that little humpy thing. Okay? So this is the rate of death of these particular objects. Okay. So this weak generational hypothesis was the basis of going generational in the first place, right? All the stuff on the left ends up in Eden. Since we do an evacuation collection, the cost of the collection is proportional to the amount of live data. And as you can see, the amount of live data is going to be very small in that particular space, so we can just evacuate a small amount of live data. So that's a huge win. Okay. But there's also something else that this thing says. This thing says that the amount of live data in your heap at any point in time is constant for some definition of constant. Okay? In other words, there's a little bit of variability here, but it's basically constant. So if we want to reduce the overhead of object copying, the answer is to do fewer collections. Right? If I do one collection every 1 second, then I incur that amount of copy cost once a second. If I do it once every 10 seconds, then I incur that amount of copy costs once every 10 seconds. Right? So how do we control the rate of collections of young generational space? Well, that's all dependent upon two things, your allocation rate and the size of Eden. Right? That's a simple formula. Whatever my allocation rate is, right, I can divide that into the size of Eden. That's going to tell me what my GC frequency is going to be. So using that particular number, I can start to say, like, okay, this is how big I want Eden to be. Right? And I can look at other metrics for the other spaces, but I can say this is how big I want those particular spaces to be. So then what's my max heap size in this scenario? Well, it's the size that Eden needs to be, plus the size that the survivor needs to be, plus the size that tenured needs to be altogether. And that's how we calculate a max heap in this particular case. Does that make sense? Okay. So what did I do with the Cassandra benchmark to lower the overhead? Well, I went in and I looked at it and it says, okay, Eden shrinks to a very small space. I don't really want that. I want to decrease the number of young generational collections I have, so that means I need to make Eden bigger. So I'll go back to that shrinkage parameter, and I'll say, I don't want it to go down to 5%. I want to only go to 10% or 20% or something like that. So it'll go down until it hits that threshold, and then it'll just stop. It won't shrink any smaller. That will decrease or slow down the garbage collector, and then I will still have the same per collection object copy costs, but overall I'll have much smaller object copy costs, right? And then that actually leads to better throughput. And so that's one thing that we can actually do with this, to help slow things down. So let's see. Yeah, so if you look at what metric was I going to show you here? Let's see. No, not that one. Too many open. Okay, I'm just going to close them then. Gets rid of one. We don't need that one. It's for the CMS collector. And that leaves, this one over here, of course. So I think this is what this log actually represents. So if we come back to the summary, let's drop this one over here. And again, I'll try to do the same trick so other people can see what's going on. You can see that really what we did was, in this case, in this particular one here, we didn't go at it too aggressively, but really the difference is the number of collections overall, and that means that summary. Yeah. So in this case here we have, where is it, Young, 864 events for the same workload here. We're actually only having 633 young generational collections, right? So overall that does give a slightly better picture, although again, it's not really going to help you on an individual basis. Like, okay, so you can see the pause time picture in this particular view here. Yeah? So, anyways, there's a lot more to be learned about this collector. There's probably a lot more I can say about this particular collector right now. I think that it's going to require you guys to actually do some experimentation on your end. If you do some experimentation, I guess you can actually see in this case that the GC log is actually going to give you a lot of useful information in terms of the type of the hints and things that you can see. That's pretty much the data that we're working from or whatever like that. But and there's other flags you can turn on to actually get more data out of it, so you can get more details as to what's going on. But I think that that's pretty much what I have to say for today, given the time that we have. So I'll leave the floor open for any questions if you guys have any questions right now. Yes, sir.
Do you have a slide comparing G1 to concurrent market sweep?
Do I have slides comparing G1 to concurrent market sweep?
How much faster it is?
How much faster it is? I don't really, I mean, I was doing this with the Cassandra benchmark. I just use the CMS collector really as a reference point to figure out what's going on in terms of overhead. In other words, I need to do more experimentation myself. I do know that the G1 is still problematic. I honestly myself question its readiness for complete prime time. It's certainly, I have moved a lot of customers to using the G1. We're currently moving a very large customer to be using the G1, and it's worked out fairly successful. But I would say that in some other cases where we used it, it's just we looked at it and said, okay, it's simply not going to work. It really depends on a case-by-case basis, unfortunately. I don't really have any guidelines yet.
And what about memory leaks? Does it have any memory leaks?
Memory leaks? That's a different issue altogether. That's a bug in your application, right? But I mean, in terms of the JVM leaking memory, no, there are no memory leaks. I mean, the memory leak picture in 8 and 9 is going to look completely different than it did in 7.6.5.4 and all the way back, simply because we moved from perm space to metaspace. And metaspace looks more like a Java heap space. Sorry, perm space looks more like a Java heap space. Metaspace looks like a C space, right? So C space leaks are going to have, when you get a metaspace leak, it's going to look like a C space leak. Where before, when you had like a perm space leak, it looked like a Java heap space leak. So, but in terms of the actual collector itself, no. The floating garbage problem, I think, is huge. But that's not a leak per se. Yeah, that's loitering, which is completely a different problem. Any other questions? Yes, you in the back? What about small heap sizes? Yeah, that's a good question. Small heap sizes tend to come with machines that have small number of cores. And I think that's really kind of like a bigger issue. For instance, if you're running this type of stuff on your Raspberry Pi, I haven't done much benchmarking on a Pi in terms of G1 yet to actually see how it would perform. But like if you're like on a single core, forget it. I wouldn't even bother. In that case, you're better off using a serial collector. The serial collector is the lowest overhead, fastest collector that's in the JVM, right? It's just serial. But I've some quad core Pis that I want to play around with. In terms of with the G1, just to see what it would do, but I kind of suspect that this thing here just wants cores, and it certainly wants power, right? In terms of memory, I I don't know how small you'd want to go with it, before it would not be really effective. Quite frankly, anything below 2 to 3 gigs in heap, it's much better to use a parallel collector anyways, or even a CMS collector. You're just going to get much better. You're not going to get any advantage, I think, using a G1 collector. Okay. Any other questions? Sorry, I can't see anybody on the top if you are asking. I guess not. And we're out of time. So thank you all for listening and enjoy the conference.